Okay, so this is chapter 2, matchings, or matching as an activity. And if you think you know what matchings or matching is, then you're right. So the classical approach is that you have a set of boys and you have a set of girls, and for every boy you put an edge to every girl that he swiped right, and for every girl you send an edge to the boys she swiped right, and then what you want is a match of as many pairs as possible. All right, something like that. And so a matching is any independent set of edges in a graph. So, as in modern times, the graph doesn't have to be bipartite. You still want to find a set of as many pairs as possible, and independent just means pairwise non-adjacent for edges, right? For vertices as well. Okay, so independent obviously has many meanings in mathematics. In graph theory, it means pairwise non-adjacent. Okay, so a matching is any independent set of edges in a given graph, bipartite or not. And there are practical questions, like given a graph, how can my computer find a largest matching? We'll be able to deal with those rather quickly. And then there are theoretical questions of two types. One is, can we relate the size of a largest matching to some other structural properties of the given graph? That will concern us most. And one particular question, when the graph is bipartite, so with classes A and B conventionally, then the particular question of does there exist a matching that covers all the vertices in A is one that has been investigated and solved. And so the classical application would be, these are jobs to be done. These are people that can do the jobs. I mean, not everybody can do every job, but some people can do some jobs. And can we get all the jobs done by assigning some suitable people to each of the jobs, a person to each of the jobs? Right, so that's a particular problem for bipartite graphs, and also on the theoretical side, can we identify theorems that tell us when there exists a matching of all of A? Okay, and we'll get to some such theorems today. Now, for today, all graphs we consider will always be bipartite, and they will have classes A and B. And then let's address the practical question first. How can we find a matching of maximum size, right? As many independent edges as possible? So, for example, we might have our graph with some edges here, and then we might do it greedily and just collect independent edges, one after the other. So we start with this edge first, and then when we've taken this, then we might be considering this edge and say, oh no, I can't take that because that's not independent here. And then we might consider this edge and say, oh no, we can't take that either because that's not independent here. Oh, I wish I hadn't taken that one, right? Because the white edges are a bigger matching than the blue edges. There's something to be learned from this tiny little example, and that is it shows what will be called an augmenting path. So if I do this zigzag here and toggle membership in the matching, so edges that were not in the matching get put in and things that were in the matching get thrown out, then this toggle increases the size of the matching. Right? So let me write that up more formally. So an alternating path with respect to a given matching M is a path that starts in A at an unmatched vertex. So a vertex is unmatched if it's not incident with an edge in M, unmatched with respect to this particular matching here. It has to start in A with an unmatched vertex, full stop. No, sorry, and then alternates, yeah? Then alternates, hence an alternating path between edges in or not in M. So if it starts at an unmatched vertex, then obviously the first edge will be not in M, because there isn't one in M at that vertex. And then the next edge has to be in M. So, okay, let's do it here. So if we start at an unmatched vertex here, then the next edge has to be in M. And then the next edge after that would have to be outside M, so we can't continue in this case. We might continue here if this edge existed, or we might continue there. So if we continue here, then we can continue yet again with an M edge and go up to here, and then we might continue all the way there, right? So if we end up in B at an unmatched vertex, then this augmenting path is useful, and it's called, this alternating path is useful, and it's called an augmenting path. Augmenting as in increasing the size of. That's any alternating path that ends in B at an unmatched vertex. And this matched always refers to this M, right? An alternating path is called an augmenting path. If it is an alternating path, so it has to start in A at an unmatched vertex, and then it goes back and forth, not an M, in M, not an M, in M, not an M, and so on. And if it does end in B, then obviously with a not an M edge, it always gets to be on non-M edges. And that vertex, that last vertex, is unmatched, then it's called an augmenting path. And the reason is the one I showed you. If we toggle membership in M along that path, we increase the size of M. Important, we're not increasing M as a set. We're not finding a superset. We're not finding a larger set, which is why the greedy algorithm that I showed you earlier got stuck. we're not finding a larger set, we're finding a different set of larger size, a different notion. Yeah. Okay, so augmenting paths always find a bigger matching, and here's a sweeping trivial theorem. Whenever you can always find a maximum size matching just by using augmenting paths in any graph, not just bipartite graphs, but I've defined it here for bipartite graphs, so starting in there only makes sense in bipartite graphs. Otherwise, you just drop that. But say in bipartite graphs, if you have a matching and that isn't largest, doesn't have the maximum number of edges for any matching in that graph, then with respect to this matching, there exists an augmenting path that augments this particular matching and gives you a larger one. So we would just keep finding such paths and applying them, and then we'll end up with the largest possible matching. And that's that for as far as practical search for matchings is concerned. That's all I'm going to say about that. Right, you can look at the details of how exactly to find such an augmenting path and so on. We don't do that here. All right? But in principle, this is solved by just augmenting paths. Very, very simple. Yeah, questions? No. Okay. Then, on to theoretical questions. As I said, there are two types. One is how can we relate the largest size of a matching or the structure or the position of a largest possible matching in a given graph to other structural properties of that graph, particular to some graph invariance perhaps. And the second question is, when can we find a matching that covers all of A? So let me address the first question, the structural question. We'll do that for bipartite graphs today, and we'll do it for general graphs next time. Okay, so theorem. So this is a theorem of König, the same König I mentioned last time, I think. Danish König. Hungarian mathematician who wrote the first graph theory book. Let me look up the accents on the first name. Oh no, I don't have it here. I don't know. He's probably got accents. They all do. So does anybody know them? No. Okay, but he's pronounced, this is by authority, not mine, Attila's authority. Attila is upstairs and he's Hungarian. Danish. Not Dennis, Danish. And I asked him, is it König or König? And he said, König. Yeah, but it's the German word, and they pronounce it faithfully. So, right. So, his theorem says that the largest size of a matching in a given graph is equal to the smallest size of a vertex cover. Now, what's a vertex cover? That is a set of vertices meeting every edge of the entire graph. It's a set of, so given, this is, of course, for all graphs, right? So a vertex cover is a set of vertices of that graph that meets every edge. And that is a well-defined statement because an edge is a true set of vertices, right? It intersects every edge. Okay. Is that an interesting theorem? Well, if you say yes now, then you're either too polite or you're too clever. I don't find it at all interesting. So it asserts that two numbers are equal, and these numbers are, yes, okay, we're interested in how large a matching can be, perhaps. Are we interested in that? No, but maybe if that solves this, but it doesn't solve anything, it just tells us what the right number is. Or does it? Okay, here's a way of making it interesting. Let's look at these sizes of matchings and of vertex covers. So a vertex cover is a cover by vertices of edges, right? Let's look at these sizes. So if we look at the sizes of matchings in our given graph, and we look at the sizes of vertex covers, then we have this obvious inequality, right? A vertex cover must be at least as large as any matching, because we have to cover, in particular, the edges, the independent edges in this matching. And we need as many vertices to cover just those as the matching has elements, because they're all independent. Okay, so clearly any vertex cover has size at least that of any matching, and in particular, even the smallest vertex cover has size at least that of a largest matching, but there might still be a gap. And the theorem says there isn't a gap. These two numbers actually, there exists a number that satisfies both. That is the size of some vertex cover, and that is also the size of some matching. And if it is, then obviously it's the largest size of any matching, and it's the smallest size of any covered by this trivial inequality here. So the existence of this is really the theorem. And that is interesting, because that's a very, very structural assertion. That just asserts the equality of two numbers. This, what does that assert? It asserts the existence of two things in a graph. A matching, some matching, and a vertex cover of all the edges, not just the matching edges, all the edges, some vertex cover. And since they have to have the same size, we know structurally exactly what has to happen. Namely, the vertex cover has to pick one of the two vertices from each of the matching edges. So this is an existence statement. Two things have to exist. A matching has to exist, a vertex cover has to exist, with the joint property that the vertex cover consists of picking one of the two edges of any matching edge, or every matching edge. It's a very, very structural assertion. And interestingly, for infinite graphs, you can still prove that. For infinite graphs, this becomes trivial. Infinite numbers are basically all equal. Not quite, but there are very, very different graphs with all reasonable graph invariants being the same number, like countably infinite or continuum big or something like that. So just looking at cardinalities and infinite graphs is usually makes statements trivial. whereas the structural assertion is a really, really hard theorem for infinite graphs, but it's true. Okay, so that's one way of motivating this theorem. That really is a nice statement that this exists. Another way of motivating it is to say that a large matching is one particular reason for needing many vertices to cover all the edges. Right? If we have a large matching, then we need at least that many vertices to cover all the edges, because even to cover those edges, we need that many vertices. And the theorem says that this particular, very specific reason for needing many vertices in a cover actually is always there when we do need a certain number of vertices, at least, for any cover, then there exists a matching that is the reason for that, or is a sufficient reason for that. Which takes me on to certificates. Right? We had certificates for odd cycles and bipartite graphs. So an odd cycle certifies that a graph is not bipartite. And the same here. A large matching, or a matching of maximum size, certifies that a vertex cover of that size is small as possible. It can't be any smaller. And the theorem says, for an optimal vertex cover, one with the least number of vertices, there exists such a simple to verify certificate. If you are trying to sell me a vertex cover and say, yeah, I can cover all the edges, and I can say, yes, I see that you're covering all the edges, but can you make do with fewer vertices if you choose them completely differently? And then you can say, no, because here's a matching of exactly that number of independent edges as I'm using in my vertex cover. Then clearly I can't make do with fewer vertices. So I'm not telling you that it's easy to find that matching. In fact, it is, but it's a certificate once you have it. And similarly, a small vertex cover is a certificate for the maximality, or for the maximality of the size of a given matching. Now, I'm trying to tell you a matching and say, you can't have a bigger matching in this graph. And you say, oh, well, maybe if you sort of go about it in a very different way, I say, no, because here's a vertex cover that covers all the edges, not just my matching, but all the edges. With only that many vertices, then clearly you can't find a cleverer matching with more edges, because then one of them wouldn't be covered by my cover. So a cover, such an optimal cover, certifies the optimality of a matching. So you have these certificates both ways, which is another reason why this is an interesting theorem. Although it very sort of modestly comes in the shape of just the equality of two numbers. Okay, so before I move on to the proof, any questions? No. Okay, then let me prove it. So on the face of it, this just asserts the equality of two numbers, but I showed you already that it's equivalent to this existence statement there. So if the theorem is true, then for any largest matching and any smallest vertex cover, we know exactly what they look like. The vertex, well, not exactly, but we know roughly what they look like. The vertex cover has to pick one of the two vertices from each matching edge. So as an approach to the proof, let's just start with any maximum size matching. So maximum size matching. I might also say a largest matching rather than a maximal one. One like this. And then let's try to find a vertex cover that picks exactly one vertex from every matching edge, but covers not just these edges, but all the edges. And if we succeed in doing that, then we have proved the theorem. Okay, so let's start naively by taking all the left vertices into our vertex cover. Okay, might that be a cover of all the edges? Yes, maybe it might. But then it might not be. So maybe there's another edge that we haven't covered with yellow. Okay. Well, but we made a default assumption here by choosing the left vertex of this edge, which wasn't forced. So we could say, oh, okay, if such a white edge exists, we just use the other one. Yeah, that might, however, be a disservice to ourselves because this vertex was previously in the cover. Now it isn't, so there might be another edge that used to be covered and now isn't covered. Yeah, could it look like this? Precisely. This is an augmenting path, right? So that can't exist because we have a largest matching. But if it might not be an augmenting path, so it might look like this. Yeah. But then we have to put this vertex, choose that vertex from this edge. Because if we chose that vertex, then this edge would still be uncovered. So we have to choose this. And now here at this point, we can sort of, so far, our proof strategy was just mindlessly play and see what happens. And now our mind kicks in and says, oh, I've learned something. What have we learned? We have learned that any vertex on the right that we can reach by an alternating path. Okay, let me write it down. Every vertex on the right, I write in B, so this is A and this is B, that we can reach by an, by an alternating path is matched and in U. So in fact, every vertex that can be, no, fine, okay. Every vertex in B that we can reach by an alternating path has to be matched, otherwise the alternating path would be an augmenting path, and that can't exist because M is largest. So it has to be matched, and if it is matched, then it has to be in U. Why? Well, let's do the proof formally. Suppose we have an alternating path. And let's look at the first time it meets an edge in B that is not in U. It always meets the edges in B on the right first. That's because it's alternating. It starts outside the covered, outside M, and then it always hits any M edge first on the right, and then it goes back on that edge. So let's look at the first time it hits an M edge, but not in U. Then that last edge by which it arrives there has to be uncovered, right? So if we have our alternating path somehow, and then eventually it gets to, so maybe it gets to it uses many vertices on the right that are all in U. And let's look at the first time it gets to a vertex on the right that is not in U. Then that has to be matched, otherwise it would be an augmenting path. And since this is not in U, this last edge is uncovered. So yeah. In any U that does the job, any U that does the job must contain that vertex. That's what I mean here. Right? Not for an arbitrary U, obviously. For a U that does the job, we know that it must contain all the edges in B that are matched and at which some alternating path ends. Once more, any U that works has to pick exactly one vertex from every matching edge, and that's all. And we know that for a matching edge such that it arrives, such that the right-hand vertex is the last vertex of any alternating path, that has to be in U. Okay, now we're nearly there, because now we say, okay, maybe some other vertices are in B as well, not just those at which an alternating path ends, but we could say, okay, let's try and take only those vertices in B and the other vertices in A on the M edges. That's what we might just go for and see whether it works. If it doesn't work, we can look more closely and do the whole thing with left and right inverted, because this theorem here is symmetrical in A and B. So we might get the same condition the other way around, and then we can see, okay, where do those two necessary conditions overlap, and maybe that's the solution. So that's the sort of long-winded way of using this observation. But the shortcut is to say, okay, let's just take those vertices on the right that we have to take, which are those vertices on the right on matching edges at which some alternating path ends. And if at a vertex in M there is no alternating path ending on the right, then we put the other vertex in U. Okay, so ready? Let's see whether it works. Suppose we have an edge of G, and we want to show that it's covered by U. Well, if this vertex is unmatched, the left vertex, then this little path is an alternating path. So it can't be an augmenting path because M is largest. So this has to be matched. And then it must be the choice from its matching edge of a vertex in U because an alternating path ends there. So this edge E is covered. Good. other case, this vertex is matched. Okay. But either it's covered, it's in U, in which case we're happy. If it's not in U, well, then the vertex on the right is in U. And why did we put that in U? Because some alternating path ended there. But then this followed by that is also an alternating path. Now, if this vertex is unmatched, that's an augmenting path, so that can't exist. So this has to be matched. And then same argument as earlier, an alternating path ends there, it is matched, therefore it was put in U. End of proof. Yeah, so when you read the proof in the book, it's much, much shorter because I walk you through all the sort of musings one has to go through, or one might go through, in finding that proof. But I think it's probably, I hope it's now plausible how one can naively find that proof if, or could if it was an exercise rather than a theorem. Questions? No. Okay. Then let's move on to the next theorem. And this is now about matching the left-hand side, the entire left-hand side of a bipartite graph. So we have our bipartite graph again, A and B. Here's a necessary condition for the existence of a matching of the entire set A. So when I say a matching of A, I mean a matching in the graph, an independent set of edges that covers, whose union has A as a subset, right? That covers A. Okay, so if we have a subset A, S of A, and then we look at the entire set of neighbors of S in B, that set is smaller than this, all the neighbors of S. If there are fewer neighbors than elements of S, then obviously we can't even match S to anywhere in B, because these are all the vertices available as matches for vertices in S. So that can't happen. So we need, as a necessary condition for a matching that covers all the vertices in A, that for every S, so let me write it up, for every S in A, the number of neighbors has to be at least as big as the number of vertices in S, and that is known as the marriage condition. So marriage, in case you don't know that word, is the old-fashioned word for matching. And so it answers the question of when all the boys can be married off to suitable girls. Right, and it's obviously necessary, so let me show you that it's also sufficient. I mean, it's also a nice theorem in the certificate sense. So this is clearly a certificate for the non-existence of a matching of A. And the theorem says if there's no matching of A, then there exists such a certificate. You can find you can find a subset of A and just count the neighbors. And then you will see that there are not enough neighbors just for that subset. So the theorem asserts that a possible certificate is always present if matching all of A fails. Okay. So, theorem. It's Hall's theorem. So this is all early 20th century. Hall's theorem is actually later than König's theorem, but he wasn't aware of it. It's easy to deduce this from that. You might get an exercise doing that. It's also possible the other way around. Okay, so Hall's theorem from 1935 says that the marriage condition is sufficient for the existence of a matching in A in every bipartite graph AB. Okay. So let's try and prove that. And let me apply the same kind of method. We just aimlessly play for a little bit, and then we try to observe something on the way. What we're going to do is we're going to prove that for any matching, not necessarily the largest one, no, any matching, either it covers A or we can find an augmenting path. So we'll show not covering A, there exists an augmenting path. Okay, so let M be given any matching now. Let's find an augmenting path if A isn't covered. So if A isn't covered, then there's a little a that is unmatched. Okay. Let's try and find an augmenting path. If we can find a neighbor of A that isn't matched, then that's our augmenting path. Okay, so maybe we can't find that. Is it possible that we find that A has no neighbor at all? No, we're assuming the marriage condition. So little a makes a set S of cardinality 1, so it has one neighbor at least. Okay, so suppose it doesn't have a neighbor that is unmatched, so go to a matched neighbor. Okay, we're hunting for an augmenting path, so let's continue on this alternating path as long as we can. So we can't do this forever, but whenever we arrive on the right, either we have found our augmenting path if the vertex on the right is not matched, or we can go back along this matching edge. And that's always going to be a new matching edge because because we always arrive at matching edges on their right-hand vertex. Okay, so eventually we'll get stuck. So we get stuck at a vertex. Why are we getting stuck? Or let me do one more. So why are we getting stuck? Because all the neighbors of this vertex are already on the path. Okay. Let's consider the set of all these vertices on the right that we visited. On the left, there are more vertices, aren't there? Because for every vertex on the right, we moved left afterwards, and we could always do that by the assumption that we didn't have an augmenting path. So our path here contains more vertices on the left because little a is also there. So let's take the vertices on the left of our path as S, and then we know that, well, although these edges here don't go outside, don't lead to a new vertex by assumption by definition of getting stuck, some other vertex does, so this exists. Maybe that deserves a new color. Okay, so such an edge out of this set here to a new vertex that we haven't covered, that we haven't visited. Such an edge exists. Yeah. So is that useful for us? We still can't continue our alternating path, but we could continue this alternating path from here. Rather than going down there and getting stuck here, we might escape there. So that looks sort of promising. Okay, to make it formal, let A prime consist of all the vertices on A that are on some alternating path, not just the one we're trying to construct here. Full stop. Right, so the little unmatched vertex here is definitely an A prime because it is its own alternating path. Remember, alternating paths are allowed to be trivial. Okay. Then B prime are the M neighbors of vertices in A prime. Right? Now, for every M neighbor, of a vertex in A prime, these vertices in A prime to which you can get by this M edge, they're all distinct. Right, so A prime is strictly bigger than B prime because there's also some little a. But now we can use the marriage condition, which asserts that there's an edge from somewhere in A prime to somewhere outside B prime. And this edge starts on the left at a vertex, which is an A prime, and therefore, which is on some alternating path. And then we just add that and get a bigger, a longer alternating path. We would like that to be our augmenting path, so we don't want that to be matched. But it can't be matched, because if it was matched, then that would be incident with an M edge, and we could go back along that M edge. That would put that vertex in A prime and this vertex in B prime, but it isn't. Yeah. Questions? If this is too fast, don't worry. It's all written down very, very precisely and so on. Yeah. Okay, second proof. Of Hall's theorem, of the marriage theorem, as it's called. We do induction on the order of A. And that's a very, very nice proof. I mean, I don't know whether I should find it nice, because it's so simple, it sort of takes down the value of the theorem a little bit. It's very, very simple. So, but also a technique that is eminently useful in combinatorics, and especially in graph theory. It considers the possibility that there is a sub-problem which is tight, where the condition that we have available is fulfilled, but only just. So, more precisely, case one is there exists a subset S of A, and I want it to be a proper subset, such that the marriage condition is satisfied with equality. Right? So it's satisfied by assumption, but only just for this particular S, if there exists such an S. Yeah. So we have A and B. Suppose there's this S. Then the neighbors are only as many vertices of B as S has vertices in A. Right, S is smaller than A, so by induction I can assume that there's a matching here of the entire set S. Why? Well, not quite yet. I have to show that for every subset of S, it has enough neighbors. But where are the neighbors? Well, they're clearly among the neighbors of S. And by assumption, there are enough neighbors in B, and we know they must be in here. So just on here, on the induced subgraph of S and its neighbors, the marriage condition holds true. So there exists a matching up there. By induction. And now consider the rest. And I claim we can do this by induction as well. So this time we have to show that for every subset up down here, there are enough neighbors. But if there aren't, then just consider the larger set consisting of these vertices and this S, together with these few vertices and this N of S. And then this union of these two would be the entire set of neighbors of the union of these. Right? That's important. But it's too small. So the union of S and this set would violate the marriage condition for the whole graph. So that can't happen. So we can apply induction also down here. Yeah. And notice that I'm not forbidding edges up there. The argument still works if there are such edges here. I'm just considering the subset of B minus n of s as neighbors. And even there must be enough, because otherwise we could take this union, and these here, yeah, they disappear in the union. There are no edges from here to there, by definition of n of s, right? Okay, so by induction, there's also a matching down there, and we'll just put them together. Yeah. Okay, questions? No. Okay, then let me just, there are a couple of corollaries in the book. I think I want to mention only the first of them. The other one is prettier or more involved, but then it's also more special, and there are many, many special applications of the marriage theorem in combinatorics. I think it's certainly the most applied graph theory theorem in combinatorics that I've seen. I've seen it applied in all sorts of contexts, outside graph theory as well as inside. It's a very, very simple thing, but somehow this appears to be useful. And the second corollary that I'm not going to cover is Peterson's theorem about the existence of a so-called two-factor. I'll tell you what factors are next time. It's part of the course, so please read it, but the proof is that long. I just don't want to include it here. But let me include the following corollary, and that is that regular bipartite graphs have perfect matchings. So a matching in a bipartite graph is perfect if it covers both A and B. And regular, in case I haven't mentioned it yet, it means that all degrees are equal. Right? So why is that the case? Well, we'll just have to check Hall's condition, the marriage condition. And if all degrees are k for some fixed k in the entire graph, left and right, then any s must have at least as many neighbors as it has elements, because if it had fewer neighbors, so if that was the entire neighborhood of all of S, then all these edges here, k for every vertex, they all go there. But we can't distribute them over fewer vertices and still maintain the same degree. They just don't fit. So that's a pigeonhole or something. Right? So that's a nice little corollary, just by counting. Yeah. And I don't want to start matching in non-bipartite graphs. That comes next time. So I'll wind up here unless you have questions. Okay, thanks very much.